So we were looking at the microstructures of dual phase steel and trip steels, the heat treatments, the thermal cycles that we actually adapt to generate the microstructures of these advanced ISN steel, especially dual phase and trip steels. We were looking at elaborately the heat treatment, the role of alloying elements. So why do we add those alloying elements? What are the steps involved in generating ferritic martensitic microstructure dual phase, as well as the ferritic, binatic, and retain arsenic containing microstructure in trip steels, and how the isothermal binatic holding helps in stabilizing retain arsenic at room temperature. And we subsequently moved to the hot stamping process. So we looked at the thermomechanical cycles we adapt, the deformation in the austenitic region, and the role of alloying elements again in hot stamping steel, especially the role of boron. So how boron increases the hardenability. Because of that, how we can generate the martensitic microstructure upon cooling from hot stamping. Okay, so now we will move on to the next unit on welding processes. So we look at the important welding processes that are actually used in automotive industries, the basic principles of those welding processes, and what is the current state of the art in those processes in welding of advanced ISN steels. And then we will move on to the subsequent chapters. So before going into the actual details, science behind welding processes. So we look at some introduction as usual. So for example, the main question we are going to ask is what does welding do to the microstructure? Okay, so we already looked at how complex the microstructure of dual phase and trip steel. Okay, so we have to adapt various thermal cycles to generate such a beautiful microstructure which can give high strength and reasonable ductility. Okay, and we look at now how a typical weld thermal cycle is going to affect those microstructures. Can we save those microstructures so that the weld properties are equal to the base material property, if not even better than the base material property? So the big question we are going to ask now from here onwards is can we weld advanced ISN steels? If yes, how? If not, how we can improve the welding processes such a way that we get the microstructures of welded advanced ISN steels which are superior in terms of mechanical properties. Okay, so if you look at the important welding processes that are actually used in automotive industries, the majority of the welding in automotive industry is carried out either by laser welding or resistance spot welding. So I just gave two schematics. So we won't go into detail about this process now, but we will go on one by one. So if you look at the images, what you see over here, this is the typical schematic of laser beam welding. And what you see over here on the right hand side is the resistance spot welding. So the majority of welding operations in automotive industries is carried out either by laser or by resistance spot welding. So if you look at an average number of welds that are present in a car body, typical car body is it can be say either about varying from 2000 to 5000 spot welds. And so these welds are actually made in extremely rapid time and production conditions. So if you look at it in the statistics from the Welding Institute of UK, by average about 150 million welds are made every day only in European auto industries. Okay, so the trend is also moving or is coming back from the laser welding and spot welding to the advanced gas metal arc welding as well, because of lightweighting. Lightweighting also introduces complexity in terms of material thicknesses, material composition. So some of the advanced gas metals arc welding processes they are also coming up to weld especially the dissimilar joints, and also some applications we may also use gas metal arc brazing for welding advanced iron steels. But even now predominantly the welding processes that are used in automotive industries are either laser or resistance spot welds. Okay, so in average, if you could look at a body in white or a chassis, we can find somewhere between 2000 to 5000 spot welds, and these welds are supposed to be strong and stiff throughout the life cycle of the an automotive. So a car, the automotive life cycle is roughly about 300,000 kilometers. That's the actual mileage. So these 5000 welds, spot welds, what you have in auto bodies should withstand such an enormous amount of the workload is expected. So we will look at in detail about these welding processes, all three, the resistance spot welding, and laser beam welding, and some of the advanced gas metal arc welding processes that are actually getting explored to weld dissimilar advanced iron steels. First we will move on to the resistance spot weld. So I have shown you the schematic here. So the actual welding process is very simple. So what we have is two electrodes which are generally made of copper. So we keep the interfaces that are going to be welded in between two water cooled electrodes. So the electrodes are water cooled. Okay, so what you see over here is in sheet 1 and sheet 2. So it's kept top of each other, which what we know as overlap joints on overlap configuration. Okay, and then we applied some load. While applying load, we also pass a current of some amperage. So the actual values we will see in next slides. So we pass a current and we subject the actual faying interface to a load, a compression load in this case, and so while passing current, material heats up by Joule heating, and the Joule heating generated at the interface lead to the melting of the interface, and there will be coalescence of the interface leading to formation of weld, which is known as nugget. So weld nugget is formed at the faying interface by Joule heating. Okay, so there are various 1, 2, 3 numbers I have given here, and we will see in the next slide. So what are these numbers mean, and then what are the various components of the typical resistance spot welding equipment. And before going to that, so as I already explained, resistance spot welding, the main heat generation mechanism is Joule heating. Okay, so what is Joule heating is the amount of heat that is generated is equal to the amperage, the current, the magnitude of current we send in over a potential difference of V, and how long we send those current over a potential difference, that will determine the heat generation. So in this equation, Q is joules, or it can be calories as well if you are converting it. So joules are generated by passing a current of a given amperes over a potential difference of V volts for a given time. That is the amount of heat we have to generate in a typical resistance spot welding. So the main rate controlling factors are, and we can change this equation. So V equal to IR. So V can be replaced with IR because the IR can be measured easily. So then the actual heat generated and the joules is the I square R times T. So this can also be changed into watts. If you take the time to other side, then it becomes joules per second and becomes watt, then that will be I square R. So the main factors that are controlling the heat generation here is the R, which is the resistance of the circuit, and the amperage, the current you pass it in. Okay, so and that determines your the heat generation Q. Again, R is not that straightforward. No, R is not a single factor in this circuit, because if you look at the schematic of resistance spot welding, so there are various resistance that are present in this system. Okay. So, this is slightly the enlarged version of the diagram I showed you in the earlier slide. So, we have on the electrode which is copper. Okay. So, this is water cooled, so that the electrode is not actually heated up during this process. So, we have a top electrode and we have bottom electrode. And the actual faying interface, or the plates that are to be welded or sheets to be welded, they are actually kept in overlap configuration in between these water cooled copper electrodes, right. And if you look at the system, and there are typically 4 resistors present. So, for example, R1. So, R1 denotes the resistivity of the copper electrodes. Okay. So, the R1 here, and this denotes the resistivity of the electrodes. Okay. And then we have the R2. So, R2 denotes the resistance at the interface between your electrode and the sheet surface. Okay. So, if you write it on, R1 is the resistance of the electrode, R2 is the resistance of the interface between electrode and the sheet interface. Okay. And then we have another resistance R3, which is nothing but the resistance of the sheet itself. Okay. So, the R3, what you have over here, the resistance of the sheets, and the fourth one, which is actually extremely important in resistance spot welding, is the R4. The R4 is the contact resistance. Okay. So, between 2 faying interfaces. So, what is faying interfaces? Faying means the welding, getting welded interfaces. So, that is R4, and this is known as a contact resistance. And in this circuit, if you look at it, if in the system, the R4 is the maximum, and compared to the other resistance, for example, R1 is negligible because we use the oxygen free high conductivity copper electrodes. If you use them, and then the resistance of the electrode itself becomes very negligible. And the R3 as well, and compared to the R2 and R4, it is also it is not really significant. But if you look at the actual the resistance at the contact area between 2 sheets and the contact area between the interface and the electrode becomes extremely significant in this circuit. So, the R2 and R4. R4 will be the maximum and R2 the next. Okay. So, because of the increased resistance at the interface between the 2 sheets that are welded, you expect a maximum heat generation at the interface. Okay. So, the contact resistance between the interface R4 determines the actual heat generation. So, because of the increased resistance in R4, the entire heat generation is controlled by the resistivity at the interface. So, that is the contact resistance, okay, given by the surface roughness as well as the load we are applying to keep the interfaces intact. Okay. So, the various factors, surface roughness for example, or the surface morphology and the oxide layer or the galvanized layer in sheets, and all of them will determine your contact resistance at the interface. Okay. So, if you look at the previous equation, what you looked at in Q equal to I square RT. So, the R is a summation of all the resistance. So, R1 plus R2 R3 plus R4. Okay. In that you can say R1 R3 can be very small compared to R4, and this can be roughly averaged to the entire the total resistance so roughly equal to R4. So if you know the actual contact resistance R4, which can be measured experimentally, so we can calculate the amount of heat generated at the interface, which is actually determined by the R4. So I have also given an actual temperature distribution along this curve, along this schematic, and if you look at it, the temperature and far away from the interface, because the electrode is water cooled, so you expect no heating at all. But when the temperature, when you move towards the interface, the temperature increases, and there is a peak at the interface between the electrode and the sheet, that is actually determined by your R2, which is the resistance between the interface and the electrode. And then again the temperature decreases because your the R3 is now sheets are not comparable with the R2 and R4, and at the interface your temperature goes maximum, and given by the contact resistance between the interfaces. Okay. So if this is your melting point, for example, at the interface, it can go more than the melting point, leading to formation of melt at the interface, and subsequently if you increase a time and your melt grows, either increase a time or current, your melt grows and forming a weld nugget. Okay. So to sum up this slide, so the actual system resistance is governed by the 4 resistance values I have given here. R1, which is the resistance of the electrode itself, it's very negligible because we generally use the copper electrodes, and R2, the resistance between the resistance of the interface between the electrode and the sheet, and R3, which is the resistance, the bulk resistance of the sheets we are welding, and R4 is the contact resistance between the 2 fitting interfaces. Okay. In that, R4 is the rate controlling factor for heat generation, because that is the maximum, and compared to R4, R1 and R3 are negligible, and because of that now you have a maximum heat generation at the interface given by the increased resistance at the contact area between the sheets. Okay. Clear. Okay. We will move on to the again. So I just gave the schematic of the resistance and the temperature values over the cross section of the weld setup. So we have again, so the various numbers over here. So one is the resistance at the area of the electrode, and you expect least resistance because of the copper. And then at the interface between the electrode and the sheet, you have a maximum resistance, increasing resistance, and leading to the increasing temperature. Okay. And if you move inside the sheets, your the resistance of the sheets are much lower than the interface resistance, and your temperature also decreases. But at the interface between 2 sheets, you have maximum resistance given by the contact resistance, and temperature increases significantly because of that. And then system is symmetric, right. So again there will be another increasing resistance at the interface between the bottom electrode and the sheet, and then there will be an increasing resistance, increasing temperature, and then if you move forward, your electrode would dictate your temperature distribution. And generally in a practical situations, the electrodes are not heated up because of the effective water cooling you have inside the electrode. Okay. And due to that fact that the heat transfer is very effective, and that means that when you form a weld nugget by the contact resistance of the interface, and the water cooled the copper electrodes can extract heat extremely efficiently. So we need to make sure that the copper electrodes are cooled and the temperature is not increased. So in real life the situation is extremely sharp. Okay. And due to the fact that the water cooled copper electrodes extract heat very rapidly, the weld nugget that is formed during while passing the current cools extremely fast. Okay. The cooling rates of the weld nugget which is actually formed at the fairing interfaces, can cool with a cooling rate as high as 1000 Kelvin per second, and it can go even higher to several thousand Kelvin per second as well. And because of this effective cooling what we have, and the copper can extract heat much more effectively, rapidly as well. So now the situation becomes extremely critical, right? So the cooling rates what we use it over here in resistance spot welding are very rapid. So much more than what you need to form a matagetic microstructure in advanced size in steel. Okay, so the microstructure of the weld nuggets, because of this rapid cooling rate what we apply during resistance spot welding, and lead to invariably matagetic microstructure, albeit some other phases can also stabilize. We will see when you look at the welding metallurgy of advanced size steels. But now you can say that the cooling rate what we subject the weld nuggets are in the order of few thousand Kelvin per second, and this is due to the effective water cooling, water cooled copper electrodes what we actually use for welding. Okay, so to summarize, the resistance at the interfaces determine the heat generation, and you will have a peak temperatures at the fairing interfaces because of the contact resistance, the R4 what I explained in previous slides, the contact resistance between the sheets. Okay, and the cooling rates are as high as 1000 Kelvin per second, because we will have to make sure that the electrodes are cooled sufficiently. We can't melt the electrodes, right? So we cannot heat up the electrodes. So we use a water cooling channel inside the electrode, and which can lead to the effective heat extraction of the weld nugget, can lead to increasing cooling rate as high as 1000 Kelvin per second. Okay, good. So this is a cross section view of the actual the electrode and the sheet geometry. So this is upper electrode, as I explained, this is lower electrode, and this is the cross section view. Generally, if you pass a current, okay, in this direction, and then we also apply some load. Typically current varied from say varied in a few kiloamperes. So if roughly if you have say 1.2 millimeter thick plate, and if you are welding 1.2 millimeter thick plates in overlap configuration, so the amperage can be somewhere from 2 to say 6 kiloamperes. Okay, and similarly the loads what we are applying is also can be varied, and both the current and the load would determine the nugget geometry. So how the load can change, because when you apply a load you also change the contact area between the sheets. That means that you will also locally change the contact resistance. So because contact resistance is determined by the surface morphology, the air gap between the sheets. So the actual the contact resistance can also be varied in a way by the load you apply through the electrodes. Okay, so both the current as well as the load you apply can determine your nugget formation. So the typical nugget size in the resistance spot weld is an elliptical. Again, that is also determined by the resistive distribution and the heat extraction heat transfer characteristics. Generally your weld nugget shape is an elliptical, what I have drawn over here, and it forms at the middle of the electrode in a 3-dimensional cross section. It happens at the center of the nugget, generally at the center of the electrode axis. And you have a typical weld nugget with an elliptical size that formed, and it is a 3-dimensional elliptical, sort of a flying saucer, you can say, if you look at it in 3D configuration. And if you take a cross section, you see an ellipse. Okay, generally you have a long axis parallel to the seat axis, and the short axis perpendicular to the sheet thickness. Okay. So the typical the load versus current thermal cycle current cycle we apply in resistance spot welding is given in this graph. The blue color shows the your current, and here the purple color shows the your load axis. So this is actually used to weld 1.2 mm thick DP steel, and the current and the load can be changed based on the size of the weld nugget what you want to generate. Okay, so there are some limitations. You cannot keep on increasing the current because when you increase the current very high, and you may also cause some expulsion, and we will see in next classes when you look at the weld growth curves. So right now with a typical weld thermal cycle for welding 1.2 mm thick DP steel is, so we start with no load, no current, and we once the plate is placed between the electrodes in overall configuration, we apply a load. So in this case I applied about 3.5 kilonewtons. Okay, so 3.5 kilonewtons, and then upon applying a load we start passing the current. In this case I applied up to 5.5 kiloamperes, 5500 amperes over a very short duration. Okay, so in this case up to 220 milliseconds. Okay, so the process is extremely rapid because the entire weld thermal cycle, if you look at it, it's completed in less than 400 milliseconds. So that's why this process is very attractive for automotive applications, because you can make a weld in extremely rapid time. Okay, so each weld nugget, if you look at it in this case, it takes hardly half a second. Okay, so if you want to make about 5000 welds, you can make it in a few minutes. Okay, and due to this rapid welding time, this resistance spot welding is very attractive in a production environment, and we mostly use an alternating current, an AC current, and there is a very important reason why we prefer to use alternating current in resistance spot welding. We will see in the subsequent classes why AC is preferred. The AC current is generally varied somewhere, an average current in any case is in a few thousand kiloamperes. Okay, so generally it can be varied from 2 to not more than 10 kiloamperes. Okay, so as I had explained, the contact resistance, the R4, which determines the heat generation, the contact resistance between two sheets, these two faying interfaces in overlap configuration, right? And then R is the inversely proportional electrode pressure. That means that if electrode pressure is higher, okay, and then the R decreases. So that means that if you press it really hard, you also reduce, you also have, you may induce some plastic deformation at the faying interface. So then the resistance, the air resistance, and the surface morphology, your contact area becomes more coherent. So then that may lead to decreasing in the contact resistance. So as I already explained, because of the effective heat extraction by the copper electrodes from the faying interface, the cooling rate of this process is extremely fast, extremely high. And typically the cooling rate of one weld nugget from the liquid stage is in the order of 1000 Kelvin per second. Okay. And a typical current load cycle of resistance spot welding is given in this cycle. So it's already explained. So in the previous slide, what we saw is in a simple line graph where we have applied a load as well as a current over a few milliseconds, and is schematically shown in this cycle, in this slide. Okay, so in a very simplified resistance spot welding cycle, so we have initial skews time where we start applying a load. So in the previous case we applied about 3.5 kilonewtons. So we start applying a load of, say, according to previous graph, 3.5 kilonewton. Okay. So once you start applying, finish applying 3.5 kilonewton, we maintain that load throughout the well thermal cycle. And the moment you apply a load, and then there is the current. So generally, we, as I said, we apply an alternating current. We apply a current over a period which is known as a well time. Okay, and upon applying a current of in the previous case 5.5 kiloamperes. Okay, and then we hold it for some time so that the well nugget solidifies, and during the passage of this current, welding current, and we also form a well nugget by melting the interface, and then we once you upon applying current, we keep it for some time so that well nugget solidifies, and then we take it back. We move to other positions, and then cycle continues. So this is a very simplified thermal cycle. Say the RSW cycle. Okay, and this is what we shown in schematically in previous slide. Okay, but the well thermal cycle can be as complex as possible, because if you want to modify the solidifying microstructure, we may also have to apply a post pulsing or various other heat treatments we can also induce. And because of the extremely rapid application of load, as well as possibilities for application of loads as well as current, the entire cycle can be modified very rapidly still without compromising the productivity. So that is why this process becomes very attractive. We will see in subsequent slides how the modified well thermal cycles can be subjected to in a resistance spot welding case. So far, to summarize, so we looked at the important welding processes that are used in automotive industries. So there are three processes that are commonly used nowadays. The first is the resistance spot welding, and laser beam welding, and advanced gas metal arc welding, mainly to weld dissimilar weld discs. And we looked at the importance of resistance spot welding, what are the process cycles, and the main heat generation mechanism in resistance spot welding, and what are the factors that control the heat generation. And then we subsequently looked at a typical RSW resistance spot welding current and load cycle in a simplified RSW cycle. Thank you.